How you doing? I'm Mr. Rose, and as you can see, we're going to go over a little bit of calculus that we use in physics for a pretty straightforward uh, exam type of question. So you can read the question, obviously. Now you can read the question, obviously. But essentially, we have this object here. It's falling. It experiences some resistance, and we're looking for an expression to represent the gravitational force. So, and they tell us it's assumed that the gravitational force is positive, which is, kind of a weird thing for me. I don't like to do that. But that means that my coordinate system is going to be like that. So the first thing I'm going to do is, again, this is a multiple choice question. So we definitely want to just eliminate answers and find what we're looking for as fast as possible. If I look at all my answers, A is integrating, taking the antiderivative from 0 to v and 0 to t, and v is my variable there, t is my variable there, so that one's possible. 0 to t, 0 to v, but my variable here, dv, that does not match. So that is not a possible solution. This would be taking the antiderivative of essentially nothing. Everything in this expression here is a constant, according to how I'm integrating. Same thing here, from 0 to v, dt is a constant compared to v, so I know that is not an option. Again, C is possible, V is possible, but now here E, I'm taking the antiderivative again from 0 to V with respect to T, not a possible solution. So right away, just by examining, I'm down to 3 choices. So next thing I do is, I am going to try and figure out what I want to solve for, and let's just start. I'm using Newton's second law, F equals ma. 100%. I know my acceleration in terms of variables that I'm looking for, antiderivatives. I can say F is equal to m, not antiderivatives, derivatives, my change in velocity per unit time, dv dt. Now, the force in this case is represented by my free body diagram. They told me that the down direction, right, my gravitational force is positive. So I'm going to replace that with mg, there's my positive, minus kv equals m times dv dt. Now, when I'm looking at my options here, I see dt over m, even though I threw this away, dt over m, and then here m dt, m dv. So I need to make somehow this expression look like one of these. My first option, or my first choice, is I'm going to solve for dt over m. Now I'm going to throw in my antiderivative signs at the end because I know I'm taking the antiderivative. You can really do it at any point in time. I think it's just cleaner to just put them in at the end. So the first thing I'm going to do, again, as we have said before, and many people are uncomfortable with, dv dt is not a fraction. However, we can treat it as a fraction due to some implicit differentiation rules. You should be going over those in calculus. At some point, I may post a video about that. But I'm going to separate my variables, so now it's just going to be dt times mg minus kv equals mdv. All right, well, let's see. I've got a dt over here. Oops, sorry. And I want dt over m. So I'm looking for dt over m. That's easy. I'm going to divide both sides by my m. So I have dt over m times mg minus kv equals just dv. Now, at this point, sorry about that. At this point, if I want to throw in my antiderivatives, which I can do, again, if I have my dt here and a v, well, that doesn't play well together. Here I have a dv, so I know this side I'm going to integrate from 0 to v, because I'm summing up all of the parts with respect to v, which means I want to collect all of my terms that have v's in them. That's this guy right here. Here I'm integrating with respect to t, so this side is going to get my 0 to t. Now that's the real reason why we need to separate these variables, because when I take an antiderivative, if I throw this in over here, I have a dv and a dt. I can't just take one antiderivative for that. That would actually be 2 antiderivatives, which is something we're not up to yet in our course. It's actually something we very infrequently use in an introduction to physics course like that. That's usually a more advanced class. We may get to it in the second semester. Now, when I separate my variables, now I'm going to be left with, let's keep my color coding, get this all on the same page there, the antiderivative of 0 to t of dt divided by m. Well, that's good, because that matches 3 of my options that you can't see right now. We'll go back to that. Equals the antiderivative of 0 to v of dv divided by mg minus kv. Now, before I show you my options, now this is my answer in simplest terms. Before I go back and show you the options up here, based on the way that I chose to do this, if I did not eliminate those 2 choices at the beginning, now, again, I'm going to get my answer off screen, so maybe you don't remember it. If I didn't eliminate those 2 from the beginning, I did one of 2 things now. I either found the answer because I found dt over m, dt over m, dt over m. I either found that my work matches one of the answers, or I eliminated 3 choices, and now I'm left with 2. So to me, this was the most direct way to solve the answer. When I compare, I will write my final answer up here. The antiderivative from 0 to t of dt divided by m, perfect, equals the antiderivative from 0 to v of dv divided by mg minus kv, dv dt, mg minus kv, dt over m, dt over m. I found my answer. Check. All this was simple substitution. We didn't have to do any calculus. What we needed to recognize, however, again, is that when I'm taking antiderivatives, my values need to match. And then it's just simple algebra. This caused people a lot of issues because it looks big and scary. Take things slowly. This is one of the gimmies that you may see on the AP Physics exam. That's really all I wanted to go over today. If you have any questions, as always, please feel free to comment on my YouTube channel. Please feel free as well to like and subscribe. And that's all I have for us today, and you'll see me next time.